Welcome to Maths with Bob. Today we're looking at some more resisted motion under the umbrella of mechanics, and today we're looking at the inverse square law of attraction. Okay, and we're going to try and see if this little spacecraft can escape and what's its velocity, or the escape velocity, if you like. Now, the inverse square law basically states that the resistance, if you like, is proportional to 1 on x squared. This is the force, obviously. Now x is the distance from the center of the sphere. You can see here r is equal to k on x squared now, and k is sometimes referred to as the strength of the center, and we are going to be working out what k is and looking at escape velocities in a second. Okay, so let's see if I can get the pen to work. Sometimes this pen is can be a bit fussy. Okay, let's make it a bit bigger. Okay, all right. So what's happening? Oops. Okay. So the first thing is this is a situation. We have the Earth's radius r, about 6,400 kilometers. We have some sort of a gravitational attraction, if you like, k on x squared, and x is the distance from the center of the Earth. Okay, so what's the equation? Well, the equation is, okay, if you like, x double dot, the acceleration, equals minus kx squared. Why is it minus? Well, if x is positive upwards, then this is actually the attraction force is actually acting towards the center of the sphere, so it's actually negative. And we know at x is equal to r, the radius of the Earth, that we have gravity actually acting minus g. And we can actually work out what k is. K is, you can see, gr squared. We can get the equation here, x double dot equals minus gr squared on x squared. And we're going to use a variant of the acceleration. You can see here v dv dx. Okay, now v dv dx is equal to, okay, minus gr squared on x squared. And we are going to integrate, you can see here, basically the velocity is going from u, the initial velocity, to some velocity v, and the distance x is going from the surface to just a general x position. Okay, so if we integrate these expressions, see we get v squared on 2 and gr squared on x, and we substitute in the bounds, and we'll end up getting this expression here for v squared. V squared is equal to gr squared all over x plus u squared minus 2gr. Okay, so let's move on. Okay, now for the escape velocity, okay, let's try and get the pen up again, going again. This time it didn't. Let's try. Right. You see how sometimes the pen's a little bit fussy. Okay, so what's happening now? Well, we're going to try and escape. Okay, so let's see. Well, let's quickly examine this. If you like, this equation v squared equals 2gr squared on x plus u squared minus 2gr. Now, okay, as x approaches infinity, okay, we can see that gr squared on x will approach 0, and basically we end up getting the velocity will approach u squared minus 2gr. Now, if the body is going to escape, or we're going to have a positive velocity, okay, v squared is going to be greater than 0, and we're going to have this is going to infer that u squared minus 2gr is actually positive. Now, on the boundary there between it being positive and negative, it's called the escape velocity. So if u squared minus 2gr equals 0, is equal, okay, if u is equal to the square root of 2gr, this is actually called the escape velocity. Now, if I plug in some numbers, I end up getting an escape velocity for the Earth of about 11.2 kilometers a second. Now, I did actually write something under here about this. This is pretty fast, hypersonic actually. You can see here in a minute. This is actually really too quick for the Earth's atmosphere. Okay, things will burn up at that speed, but you can see here the idea is normally what will happen is you'll put the spacecraft into a low Earth orbit, and it'll be going fairly fast at that stage, and then you just need to accelerate it a bit more once it's up about 2,000 kilometers. You can see here I've actually worked out the gravity at about 2,000 kilometers is only about 5.688 meters per second. Okay, so that's how it's usually done. Okay, now let's have a quick look. Now, what happens if it doesn't escape? Well, basically, if it's not escaping, then v squared is actually less than 0. Okay, here we are. Okay, so if it's not escaping, it's obviously staying under the influence of gravity, and v squared is less than 0. Okay, that will infer that u squared minus 2gr is less than 0. And if you look at this expression, v squared equals 2gr squared all over x plus u squared minus 2gr from before, and if we just set the velocity to 0, because obviously if it's not escaping, it'll come to rest at some stage, and you can see here if you just equate that to 0, you try and make x the subject, and you'll eventually get that, okay, that x is equal to minus 2gr squared all over u squared minus 2gr. Now we can swap the signs around a bit, but if we want to work out how far above the surface of the Earth we are, we just have to obviously take off r from that x value, and eventually we'll get down here to that x is equal to u squared on r, u squared r all over 2gr minus u squared. You can see the expression there. Okay, so that's the maximum height we'll attain at a velocity, initial velocity u. Okay, well, thank you for watching, and bye for now.